Okay, in the last two lectures, we talked about imaging of dislocation, okay, or imaging of strains in the lattice and about planar defects. Okay. Today, what we will do is we will discuss about some of the types of different types of interfaces which are present in the material, because interfaces act as obstacle to moment of dislocation and gives rise to hardening. Okay. Let us first look at what are the types of interfaces which we have. There is in a polycrystalline material we have grain boundaries are there. In addition to it, we have the grain boundary itself can be classified into low angle boundary, low angle boundaries. The low angle boundary can be classified into tilt boundaries or twist boundaries. Okay, or dislocation itself sometimes are categorized into the grain boundary itself is categorized into dislocation boundaries. Then high angle boundaries are there, which are some are special type of boundaries. Okay, twin boundaries is one case that we will talk about. Some of interface boundaries and some boundaries are called coherent boundaries, some are incoherent boundaries. We will look at all these types of various types of boundaries, how these boundaries can be identified, okay, and characterized. Okay, let us first start with small angle boundaries. The small angle boundaries, the simplest case which we can think of is a tilt boundary. Okay, essentially, what are the various ways in which we can form a tilt boundary? Schematically, if we try to look at it, if we take a single crystal, okay, if we try to cut out a small portion of it, making a small angle theta, okay, and then trying to join these two together at this interface, then we will be having a boundary which comes like this, correct? And though we draw it like this, if we join them together, it looks like that. In a continuum mechanics, it looks like a continuous boundary, but essentially if we look in the atomic level, there will be some small steps will be coming, ledges will be coming. So this if we join together, then there will be dislocations which will be coming. These are all edge dislocations. They form one on top of the other. Essentially this can be considered as around this boundary plane. With respect to one side, the other side is rotated by a small angle. That way also we can define this boundary. Okay. The case which we have shown is a symmetric tilt boundary. We can have asymmetric tilt boundary, and what is important about this boundary is that rather than dislocations which are present randomly, when they align themselves one on top of the other, the elastic long range elastic stresses become 0. Okay, that's reduced. That's what essentially, this is what you can see it in Hull and Bacon's book. That's if you have a single dislocation, okay, we can see that with respect to the core 10B, 20B like this, it's a distance away from it, how the stress field is changing. Okay, if we put one on top of the other, okay, then you can see that corresponding to this, there is going to be a compressive stress on this side, but corresponding to this there will be a tensile stress. They essentially cancel each other. So finally, you find that it's a stable configuration which we have. That's what one qualifies the boundary to be a stable boundary, right? And this part of it, Marc has talked about it in detail earlier. Okay. So essentially, when we form a tilt boundary, we have only one type of a dislocation which is arranged. But what we should remember is that this dislocation could be coming from a slip plane, but the plane which it forms, okay, the boundary plane could be any plane. Okay. And if we have another type of a dislocation which is present, okay, which is also coming, then the boundary could be an asymmetric boundary, that tilt will come. Okay. And we also know that that same thing can be considered as in a material. If we have one single dislocation is present, we know that when we have added one, there is a slight tilt is going to happen on either side of it around the boundary. Okay. and if we increase the dislocation density on that plane, the boundary angle or the misorientation is going to increase, correct. So, that this is given in detail. Okay. With respect to the misorientation, the boundary angle increases. It does not increase infinitely, because when we consider the tilt of about 10 to 15 degrees, essentially that is the time when the core of the dislocations merge. Then we can't say that we are seeing a dislocation there. The distinct dislocations could be seen only when the angle is less than 10 degrees. Okay. All these aspects you have studied. Okay. Now, what I will do is I will show both tilt and twist boundaries in an ordered system in which we have done some work. Okay. Essentially, this is a gamma TAL alloy in which the high temperature phase is a HCP phase. Okay. So, basal plane is there, and the basal plane, and it transforms into a structure which is very close to FCC, ordered FCC, you can say L10 structure. Okay. If we have a BCC, not BC, HCP in which if an FCC structure forms, how many ways in which the structure can form? Can tell me? Because then on one basal plane, then another plane has to come. That's how it will happen, right? How many ways in which it can form? From FCC to go to HCP, if you go, how many we can come? How many variants we can have on HCP in an FCC single crystal if you try to do? That 4 planes are there, so minimum 4. Now here in HCP to FCC, no, HCP has got only one basal plane, a single crystal, in which it can form with a stacking sequence ABC, or it can come with a stacking sequence BCA. So, one is a twin of the other. So, we can have essentially 2 variants of FCC can form on HCP. Okay. That is what it will happen. And here what happens when it is an ordered one, okay. Here we can have essentially 6 variants. That is because in this particular lattice, along one-on-one plane, if we look at it, the threefold symmetry is lost. Okay. So, this is what is being shown here. This is for an ordered HCP, but you assume that this is disordered, all will be of the yellow color, this one. With respect to this, when the ordered one, the gamma lattice forms, okay, what you can see is that it can form with this ordered layer arranged in this direction, or in this direction, or in this direction, all are equivalent, correct? But with respect to this lattice, they are distinct because there is an ordering which is there. If ordering is not there, they will turn out to be the same. And these colors essentially say that, though since its one layer is being shown, if this has got an ABC stacking sequence, this will have an BCA stacking sequence. So, one is a twin of the other. And all these variants can form, okay, one adjacent to each other. They will give rise to different type of interfaces. Okay. And generally, when this gamma lattice forms, okay, gamma TAL, the C by A ratio is slightly less than 1. Because the C by A ratio is slightly less than 1, it will give rise to some sort of a symmetric tilt boundaries will come because of that, both twist and tilt boundaries. Okay. Essentially, what is shown here is that all the variants which will form, which has been imaged in an electron microscope and then it has been indexed, okay, this is what is being written O1, O2, some order number has been given depending upon that orientation. Okay. But what is essentially important is that I call one as an orientation, that is what it is being shown here, is the closed packed plane of the HCP lattice, and the ordered lattice is being shown because it is right tetragonal distortion. The angles, if you see, these are all 60.33, this angle is slightly less, whereas in a 111 direction or 001 basal direction, all the angles have to be equal. So, the possibility which it has is that it can form with its one of its direction either coinciding with this or it can coincide with this. So, that means that these two orientations when they form with respect to the HCP lattice, they are slightly tilted. Okay. Now, you assume that in this HCP lattice ordering is taking place. A nuclei is formed at this point and nuclei is formed at another point which is away from it, and they come and join together. Then what is essentially is going to happen? There will be a slight misorientation between both of them. That will give rise to a boundary. It's like a symmetric tilt boundary. That's what it forms. This, if you look at it, you can see that this tilt boundary, these are all the dislocations which are present on this boundary. Okay. How one can identify these are tilt boundaries? What I have not shown here is that from the same region under different tilt conditions, okay, diffraction patterns have been taken on either side. Okay. They show a small misorientation, which I will show next in the next case, in the case of twist boundary, okay, with which we can try to identify. Then we have to analyze it, what is the boundary plane and all these things. As I had explained, to fully characterize the dislocation, we have to use G dot B invisibility criterion to find out, and then using stereographic projection, one has to find out the line direction and the fault plane. That's what has been done. And then we know what are the dislocations which are present and what is the spacing between them, also could be determined from this micrograph. From this spacing, I can calculate what is the misorientation angle when the dislocations are present like this. Okay. Because essentially what we write, theta will be equal to, I think, B by H, the spacing between them, correct? So, with that, when it has been calculated, the angle turns out to be very close to the misorientation angle which is expected from the crystallography, from the crystal structure. Okay. That tells us that this analysis is correct. Here, if you look at it, in this boundary, this is one set of dislocations are present. Here, if you see, there is another set of dislocations are also present on the boundary. Because of this, you have seen that the boundary plane has tilted. Okay. It has become from a symmetric to an asymmetric case, it becomes. Then, before we go further, before I go to twist boundary, this is what I am looking at it, is that if I look at that interface between two variants of gamma, depending upon the orientations which I had mentioned, various types of interfaces which can come. One in which, if you look here, the glide plane remains that same with respect to this boundary. If you see here, this is the direction in which the minority atoms are there. Here the minority atom direction is slightly rotated. So, that is why this sort of domain interfaces where across the boundary there is a rotation by 120 degree, they are called as ordered domain interface or 120 degree rotational interface. This is another one where this is essentially across this boundary. If you see this one glide plane, there is a mirror plane which is going to be there. It is a mirror image of this. When such a thing happens, these are all called as true twin interfaces where there is a 180 degree rotation. And here if you see it in this interface, this and this is a mirror plane, these two planes, but you look for the position of the atoms, they are rotated. These are called as pseudo twins. Okay. There are various classifications comes in ordered alloys. Okay. But essentially just to show that, but if you forget about the order, essentially these are all twins only. Okay. So, here, but because in this material the crystal structure, the C by A ratio is not equal to 1, because of that between two variants, that 120 degree boundary, you can see that there is an array of dislocations are there, okay, which have formed, and these dislocations have split into partials. Okay. So, this is another type of a boundary which it can be there, where it looks like a plane. This is one which is peculiar to ordered lattice. That is one of the reason, compared to a disordered material, when it orders, even within a single crystal, you have so many types of interfaces which are generated. All of them act as obstacle to dislocation motion. Okay. In addition to the diffusion being slow in that, because of that it leads to hardening. Okay. So, A twist boundary is essentially where we have one cylinder and cut that cylinder into half, you rotate it slightly and then join them together by a small angle. Then to make an accommodation across it, okay, there will be a boundary, some dislocations will be formed. But what is going to happen is that tilt boundary, when there one dislocation is sitting on top of the other, they are in an equilibrium position, whereas here if you just rotate it, you can just go on rotating it unless and until you give an opposite force to stop it somewhere, right. Some torque has to be given to get the boundary arrested. So, because of this, one set of dislocation cannot form a twist boundary. We require one and another one opposite. So, both together decide the equilibrium position. That you will always see that twist boundary will have two sets of dislocation perpendicular to each other. Okay. That is what essentially is being shown here, okay, where two layers are twisted and arranged, then the atoms rearrange themselves to an equilibrium position where have a dislocation. This is one, there is a network of dislocations in BCCN. Okay. Here also you can see these dislocations have arranged into some hexagonal structure. Okay. This I had already mentioned. Okay. Okay. How twist boundary forms in this particular alloy gamma TL. Essentially, now you see that same one-on-one plane we are showing it here. Okay. You look at this is the ordered one, where essentially we have one set of the one particular variant which is there, and that same variant can be slightly shifted, right. If this one variant comes on top of it, that is if a nuclei of this variant takes place here, another takes place, both grow in the direction perpendicular to one, they come and join, there will be a misorientation which will come. So, that boundary is essentially a twist boundary. Okay. That is what essentially happens in this particular case. Okay. This is the microstructure, okay, where if you see in this region as well as in this region, it is the same variant, but there is a boundary which comes in between them. Okay. Right. If you look at it, both the sides, you are seeing the same, you can say that it is like something like some grain, but one boundary is coming in between. Okay. If I tilt it, immediately I can see that there are two sets of dislocations are present. This is one, another one is not present very clearly. I will show it later, another tilt condition it could be seen. And if you see these diffraction patterns which are taken, the spots appear the same, right, in both the cases. But if you look here, you can see some faint in the background intensity could be seen. This faint background intensity between this and this, if you see here, it is symmetrical with respect to a central spot, here it is shifted slightly away. These are essentially what is called as Kukuchi bands. These Kukuchi bands are the ones which are used to find out the deviation from the exact Bragg condition. Okay. Like Kukuchi bands which you see in EBSD, exactly the same type of a band which you can see it. They will be very faint, and one property in a microscope essentially is that these Kukuchi bands, if we tilt the sample, they are very sensitive to tilt because the origin of the Kukuchi band is within the sample itself. So, the sensitivity is about something like less than 0.25 degree. So, because of that, using this shift, I can immediately find out what is going to be the shift from this region to another region. Okay. Then that same region has been imaged under different conditions. Okay. This is taken under beam direction which is 112, then under our beam directions like that is what is being shown, 001 it has been taken. Okay. So many other beam directions it has been taken. And since it is an 111 plane, I have taken a stereograph of 111 plane and try to project all the directions, and from this could calculate, okay, that part I am not going to use. We can find out what is going to be the exact shift which is going to be there. Here again the twist, the angle if you look at it, that turns out to be 0.6 degree, which is what essentially it turns out from the crystallographic consideration. Okay. This is in some of the boundaries, you can see now here that there are one type of a dislocation which is present, which is imaged in weak beam, and this is the other type of a dislocation which could be. So, it is essentially a network of dislocation which has formed, okay, which are perpendicular to each other. And these dislocations are also have been analyzed, okay, and it has been seen that in this particular one the dislocations are half 112 bar, and in this particular case it is half 11 bar 0. These will be Burgess vectors are perpendicular to each other. This sort of dislocations, okay, is the one which is balancing the other. With this network, okay, we can have a twist boundary which is forming in this alloy system. Is this clear? So, this is one particular way in which a twist boundary can form. Twist boundary can form at as a sub boundary at high temperature creep deformation or high temperature test as well. Okay, that I will come later. Okay. Similarly, this is another case in this alloy. What is happening is that there is a very small twin layer has formed, okay, an ordered layer, and that ordered layer is receding. So, when it is receding, because of the strains which are present around the twin, one can see that there are a lot of dislocation. In this picture you can't see it, but the magnified view if you see it, these are all the twin region which is taken from this region. In this region where the twin has tapered, it is almost come to an end, okay. Then very far away from it, when you see, you do not see dislocations, and essentially the same boundary, because where the twist boundary is parallel to the beam, now it is tilted, and when it is tilted we can see two sets of dislocations. These have been analyzed. From this we can find out what is the network of dislocations, and from the spacing between the dislocations, okay, we can try to calculate what is the twist angle. That is essentially what has been done in this case. Okay. So, what I had shown here is in this one is a tilt boundary which we see in this one, the summary of what all types of boundaries which we have seen, and another is a twist boundary. Another is when, as I mentioned, that with respect to the HCP structure, FCC structure is forming on either side. So, either side when it forms, there could be a small misorientation which can come. Suppose the HCP structure dissolves, then with that misorientation a boundary will form. That is what this boundary is called, dissolution of alpha 2. And another is when a twin also is receding, that will also evolve. So, there are various ways in which this boundary can form during heat treatment in materials. Okay. You have studied this twinning in FCC. Twinning in FCC, you know that. So, essentially by giving a homogeneous shear of essentially A by 6, 112 bar is the dislocation, and the shear vector is around 0.707. Shear is very high for FCC to create a twin. Okay. With this shear vector, atoms will be shifted, and this is this plane we call it as the composition plane or the coherent twin plane, okay, and this is a mirror image of the other. Okay. The effect of this will be seen in the diffraction also. That is how we identify the twins. Okay. I will come to that. Before that, there are various ways in which types of boundaries, other than that, many symmetric boundaries other than twin boundaries which it can form. We call it as that sigma equals 3, that is coincident site lattice model if we use, okay, depending upon you take one lattice, rotate it gradually by different angles, find out how many atoms are coinciding. That is how we find out what is the total number of atoms which you have considered. On that basis we write, find out the, whenever the coincidence is going to be maximum, then that boundary is going to be stable compared to other boundaries. So, energy will be less. Okay. That is what we essentially see here. If you do not consider the special boundary, this is how the energy will be changing as a function of misorientation. And now you find that there are at many particular angles, you find that the energy is decreasing, correct. So, twin boundary is also a special boundary where the boundary energy is very small. Okay. This I had just explained. Okay. This is a twin boundary, and here what has happened is that the sample is being deformed. You can see that some dislocations have entered into this boundary. Okay. I will we have done a detailed analysis, I am not going into it, but you can see that the dislocation brings about a small shift in that image, okay, and essentially this dislocation can move on this boundary plane also, okay, and depending upon the stresses which they create, either on the other side they can create some dislocations, and that is how it propagates deformation across the boundary. Okay. How to identify twin boundaries? Okay, that's very important. Generally, the normal practice, we think that any boundary which looks straight, parallel, we say that it's a twin boundary. That need not be the case. Okay. Here, what we have done it is that this one, you can assume it to be a grain. It's actually an ordered one, where you can see the boundary, and this boundary is sharp because it has been made parallel to a beam direction. When I take a diffraction pattern across this boundary, okay, the image which I had shown, that is corresponding to projection which is 110 type projection. In this projection, if you see these parts all together, okay, this one, okay, then corresponding to that this one, all of them together form the 110 type of a lattice. And since it is a twin boundary which is like a reflection, I can put this plane perpendicular to 111 plane is this one, parallel to this boundary, and when I reflect this diffraction pattern, I get the pattern corresponding to that. So essentially, whatever it is happening in that sample, as we have seen, one side of the twin is a reflection across the boundary on the other side. Okay. In the diffraction pattern also, the diffraction pattern corresponding to that also get reflected. So one has to verify, taking a diffraction pattern, making first the plane parallel to the beam direction, okay, then only we can say that this boundary is a coherent twin boundary. Okay. These are all some of these boundaries which are essentially tilted coherent twin boundary. Okay. But if you look here, here also it is a tilted boundary, and these segments which are coming are called as incoherent boundaries. Generally, those incoherent segments will have a lot of dislocations which are associated with it. Okay, it's not very clear in this picture. Okay. So what we have covered is tilt boundary and twist boundary and a twin boundary. These are all the boundaries which we see in. Then grains, when we consider, they are high angle boundaries. Okay. So from one grain to another grain, if we have to go, if we fix the unit cell directions, then we have to rotate through 3 angles to get it. Okay. Plus the plane which is coming, plane normal, also should have 2 directions, it's being a vector. So essentially, that's why we say that 5 independent systems which has to be there. Okay. Define the boundary. And the grain boundary misorientation we can find out. And generally, grain boundary is a very complicated defect. It's not that easy to characterize or even model a boundary is really tough. Okay. And in some simple cases, okay, this is a particular case in which the one side of the grain boundary satisfies a 2 beam condition, other side of the boundary, if you see it is not satisfying a 2 beam condition. So it means that this boundary is essentially like a lead shape. So you assume that this region satisfies 2 beam condition, this region. So across this boundary, this will give rise to a fringe contrast. That's what we are seeing. And some dislocations which are coming, being stopped at the boundary on either side. Okay. One can do all the analysis of it. Other than that, when precipitation takes place, okay, precipitates need not always be coherent. Okay. When the precipitates are semi-coherent, okay, we can have some dislocations at the interface. Okay. This is one picture which I showed in the first class, okay, or the second lecture, that there is a fringe contrast which we can see. In addition to a fringe contrast, if you see, there are some contrast which could be seen. This comes because if you look at it, it looks like some dislocations are attached to it. Okay, these dislocations are called as interface dislocations. These dislocations can form during the precipitation. Okay, that is one particular case. There is another case in which these dislocations can form is that the precipitate appears coherent when we do a creep test, especially that is where you can see that. Then depending upon the sign of the strain and the bias vector of the dislocation can get attracted towards the boundary and it can get stuck there. Okay. This is in the same alloy. Okay. You can see these dislocations which are there. This we have analyzed it. Okay. But what is essentially important is that these dislocations, if I try to heat this sample, okay, these dislocations will not move because these are essentially a misfit dislocations which are formed on the surface. They just remain attached to it. Okay. That is the way one can do it is that slightly increase the beam current. Okay, locally it may get heated, then you can see that what happens. But in a sample where contains dislocations on a glide plane they are lying, when you just increase the beam current, you can see the dislocation starts moving in the sample. Okay. This is one where during creep test, you can see that the dislocations have got attached to a surface. This is on 1-on-1 surface, okay, and they have split into some partials also, a hexagonal network which has formed. Okay, this is from the work of Dew and all. It has come recently in scientific reports, and they have tried to analyze and found out what these bias vector of these dislocations are. Okay, if you do a tensile deformation, okay, then we will talk about now after just showing what are the types of. But if you look at it, all these dislocations, unless you do a careful analysis, you will not be able to find out because all of them are on the precipitate also there is a sort of dislocations which are present. Okay, they are arranged in a regular periodic way. One has to analyze it to find out what those dislocations are, for which one should know what the crystal structure is. Okay, how is it oriented with respect to other region, whether it can be like if you remember earlier we have seen that if there is a slight misorient between two crystals, okay, then Moira fringe contrast can come. So we have to identify that the fringes of the various types which we see are the dislocations. We should make sure that they are, that one has to correlate with the crystallographic analysis, because we do, before we look at that sample, we know that when a phase transformation is occurring from one phase to another phase which it forms. So with respect to a matrix, this is the sort of a misfit which is occurring on the surface with respect to a phase it forms. Okay. If this misfit is present, we can immediately calculate, like for coherent interface, what is the sort of misfit dislocations, whether the separation matches with that, and with respect to that interface, okay, whether the dislocations which we are seeing, okay, whether they have that same bias vector and the separation, and on the plane which corresponds to that. All this information we can analyze it and find out from the TEM. That has to be done. What I am showing it is only just end result of some pictures, but beyond this there is a lot of analysis which has gone into it to put one picture. Okay. This is this is a nickel based superalloy which has been deformed, okay, in tensile deformation. If you see here, this is close to room temperature. Okay. As the temperature has been increased, okay, then you can say this 400 and this is 500. You can see that some of these regions, okay, free of dislocations, right. This is essentially a tendency to form a cell wall. What is cell wall essentially is that the dislocations, the configurant, they try to rearrange themselves. Okay. But if you look at this boundary, it is essentially some of the dislocations are blocked by the others, like a forest dislocation. Okay. They are not rearranged themselves into any particular configuration. Okay. But this is what is called as a cell wall. The same thing I will show you. This is in a crept sample. Okay. here if you see that the creep experience, the stainless steel sample which has been creep test was performed at 823 degrees Kelvin and 295 megapascal, and the total rupture life was around 700. You can see this sort of cell walls which could be seen. Okay. And again, when the at the same temperature, when the stress has been lowered, creep stress, you can see that the life has increased, but still it is that same way it's appearing. And when the stress has been lowered to 215 MPa, and the rupture life has increased considerably, but here you see some, because the dislocation density, because the stress also determines how much of dislocations are going to be generated. Only few dislocations are there, okay, and essentially they are randomly distributed in the sample, okay. When I raise the temperature here, it's to 873 K. Okay. Here you can see that some sort of a boundary they are trying to form within them, okay. And these boundaries essentially have elongated shape, because this is for 245 MPa and this is for a stress which is 215 MPa, okay. And here again you can see that when the stress is lowered, since the temperature has been raised, you see that the dislocations are rearranging themselves not only into a wall, okay, they rearrange them within the walls and form a regular periodic pattern. Okay. These boundaries normally we call it a sub-boundaries. When we say a sub-boundary, it is essentially a boundary which has arranged into some equilibrium configuration, whereas the cell walls, which they are not an equilibrium defect. They can have any orientation, okay, and you will not find any periodic arrangement in those walls. In addition to it, here lot of carbide precipitates have also formed in these alloys. When the temperature has been raised to 923 K, okay, it has been raised. Now you can see this sub-boundaries very clearly, and some of the boundaries, when it is tilted, you can see that they are arranged into some sort of a periodic arrangement, okay. That is what this happens only at high temperatures, okay. Another thing which is very important is that we talked a lot about in the last 4 days about dipoles, right. In a microscope, how do you identify it's a dipole, okay. What can happen is that in a sample which contains second phase particles, okay, like gamma prime in superalloys. So, there also pairs of dislocations pass through the precipitate, okay, and give rise to groups of dislocations, right. So, essentially what will happen is that in that case also we have two dislocations which we see, okay. What is the difference between two dislocations in a dipole, and if this is a dipole, what will be the nature of the Burgers vectors? One will be B, another will be minus B, correct? Is it not? If it is not a dipole, if it is a pair of dislocations, then this will have Burgers vector B and this will also have a Burgers vector B, correct? That is right. So, if these are all the type of dislocations which are there, if we try to look at how these atomic planes will look like, this is how it will come. This is how a dipole will look like. One is B and another is minus B. When a beam enters in this way, parallel beam passing through this, it will be scattered in this direction, okay. From here, if you see this, okay, then from here it will be scattered in this direction. You will be seeing scattering from these directions, correct? This is what it is going to happen. The effect of it will be that one is a plus G and another is a minus G. The effect is, when you see the spacing between the dislocations, in one case, as I mentioned earlier, that is, we never see the image which we see is essentially not the actual image of the dislocation. On either side of it only we see that image. So, if it is a plus B, an image comes on this side, minus B will come on the other side. So, the spacing looks at. When we reverse the G vector, it is equal to B, then you find that one image will come, another image will come. So, the spacing between the dislocation will be different. That is what it is being shown. One is G and another is minus G. You see that this looks like two dislocations. If we do a G dot B condition, invisibly both of them will be invisible. So, from that we cannot say that which has got a bias vector positive, because both G dot B will be 0, G dot minus B also will be 0. So, only way we can distinguish between them is looking at the separation. Okay. This way we can identify whether they are dipoles or whether they are going to be pairs of dislocations or groups of dislocations. Okay. So, when we do experiment in a microscopy, we wanted to get some information. So, all these analysis has to be inherently, one has to do it to get correct information about the microstructure which is present in the sample. Okay. And then there are other information which one has to keep it in mind when one do an analysis of a sample, is that what we are looking at it is essentially a very small region from a bulk sample, correct? That we have a large sample. Okay, we may be cutting a very small thin region, slice it, and from this we prepare a sample, and essentially we are going to see some thin region which is essentially 100 nanometers from that area, correct? So, yes, whatever the information which is 3D information which is available, that projection is what we are seeing it. Quite often what may happen is that the source of whatever is the things which, whatever the effect which we are seeing in the foil may not be present in the foil itself. This is one example. If you look at it here, okay, these are some faults which have formed. You can see that formed due to some dislocations. Okay, you can see that the dislocations have come and hitting this surface of the boundary, and the dislocations are hitting on this side also. And what we noticed is that we could not see any frankly dislocation source within this boundary. Okay. Then we thought that the way this sort of a microstructure could form is only by a sample where this is a sort of a foil. Okay. The source may be outside of the source is in the bulk, but not in the thin foil, but the effect is what we are seeing it. Okay. This happens quite often. Okay. So, in fact, when one wants to see large area of or large length of a dislocation within that foil, okay, the best to do is, one precaution which one has to take is cut the sample at 45 degrees with respect to loading axis. Okay. So, if we try to slice sample at 45 degrees with respect to a loading axis, what we know that with respect to that axis, some of the grains if we see, okay, that angle corresponds to the maximum Schmidt factor, correct? And that plane is turning out to be parallel to the foil surface. If one unknown plane corresponding to that is there in that foil, then the chance of seeing a large length of dislocation within the sample will be there. That is why when Marc has shown some of those pictures where you can see large dislocations, those foils were all prepared under specific orientations. It is not just randomly samples have been cut. Okay. That is what normally is done to prepare. This precaution one has to always take to get that foil, the best sample. Okay. Then another thing also which normally happens is that most of the time we always have a tendency that when you look at a sample, you see lot of features. We always see the feature which we feel we can analyze it, we will try to look at it and try to give an explanation only based on that. That is something which tendency which one has to avoid. This is a normal tendency which all of us have. You have to get out of that. I will show you in the next that examples where this is what it happens. Okay, that should never happen. Yeah. Yeah, these are all another variant of that same phase. This is an ordered nickel 3 vanadium which has a tetragonal structure. It has 3 variants are there with a twin related variants. These are some of those variants which are cutting through them. That is what essentially it is. I did not go into it because it's a more complicated structure to make them understand. But essentially the main emphasis which I wanted to make is that one has to be careful about the structure which we see, and we should always know that only a part of what we are seeing. This is one which I had given. Okay, this is some stacking faults which has been imaged under different conditions. Okay, you know stacking faults will in FCC structure on which planes they will lie, right? I had given the diffraction pattern corresponding to this with that orientation. This is the pattern in which two beam conditions have been made with some of these reflections, okay, with which these images have been obtained. Okay, you can see that for some particular reflection, the stacking fault is absent. Now I want you people to find out which is the reflection for which this stacking fault is absent. What are the possible reflections which could have given this fault visibility? What it could be? Okay, this is what the situation, because this is the experimental result. What I have got it is only this result. Now I have to analyze it and find out what it is. Okay, I had shown earlier the last class some examples where everything has been analyzed. Now I am giving a situation where the analysis has to be done, experiment is over. See, what is the condition? G dot R, okay, alpha equals 2 pi G dot R, okay, this should be equal to 2 pi R 0, correct? That is the condition for invisibility condition, G dot R has to be, right? So, what is R in most of the cases? R for stacking faults is 1 by 3, 1 1 1, correct? Plus minus 1 by 3, 1 1 1 will be the R, okay. You assume that then what is the reflections which you have got? So, with respect to either 2 0 0 or 0 to 0, if you take those two reflections, always alpha will be non-zero. So, the fringes will be visible. So, these three ones where the fringes are visible, they are always corresponding to that condition, right? And if I take in this one, if this is, what is this part will be 2 to 0, okay, this one will be 2 2 bar 0, right, if we index this by vector addition. So, if I take with 2 2 bar 0, what will happen here? G dot R, this is 2 2 bar 0, okay, to dot product with 1 1 1, this will become 0, na, correct? So, that is the one for which, so that means that this one corresponds to that, the other three corresponds to, another one will correspond to 2 to 0. So, that is how it has been done. So, essentially one has to do this sort of analysis after getting the micrograph, okay, then only one will be able to analyze it and find out what is going to be the exact fault vector. The same is true with dislocations also, okay. what I will do is, I will stop here. Okay. Essentially, I had just showed how, only for small angle boundary, twin boundary and the tilt boundary, how exactly an analysis has to be done. I had shown that. So, in those boundaries, we have to take diffraction patterns at the different orientations, okay, and an analysis has to be carried out. Okay. You have to remember at least this, how exactly that analysis has to be done, that when you do microscopy you will learn that process of how to do that analysis. As students you are supposed to learn it when you do microscopy. Okay. Then you will be able to analyze by methods which are given in the books, okay, and what the fault vector is. That it looks like a tedious task, but that is, there is, when you do microscopy there is no other alternative. This is the way you have to go about and do it. Okay. Yes. Yeah. 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 Yes, they can be done. What essentially has to be done is that in such cases, suppose the dislocations are there like this, VCS2 dislocations, okay, and if I tilt the sample along the dislocation line, if I take the axis of rotation and tilt the sample like this in this direction, we can make the beam, these two dislocations, the plane containing them parallel to the beam direction. Okay. If they are on two parallel planes, then you will find that still these two dislocations will be in two different ones. Otherwise, they will be merging together into one. No, that is what I said. Some case studies I will show where this sort of analysis has been done, where I will go into detail taking some region, how it has been tilted under various conditions to identify the various types of defects, like what is that KSW fault. In case, no, that is not KSW, what is that? Kears-Willdorf, KW faults, okay, not Kears-Willdorf, okay. Now, how you identify all these, okay, in which plane they are lying, okay. Suppose there are some kinks are going to be there, how these things are done, okay. Sometimes what happens, it looks like 2-1, at that point, some point they have made a kink, okay. All these things you could identify. That is a sample when we look at it. When naturally, when we, this is with one diffraction pattern it has been analyzed, but at least some orientation you have to tilt it. When you tilt that, you will automatically find that these faults will become, can become parallel to a beam direction, okay. That is one orientation alone is not sufficient to get a complete analysis. 2 or 3 orientations we have to, symmetric orientations we have to image the sample, okay. In addition to it, we may not be imaging them, but we will tilt it to different positions where we wanted to verify some aspects of it, like to find out whether the dislocations are lying on the same plane. Like if overlap fringes are there, then if you try to tilt this and make the ones parallel, okay, then you can very clearly see that from that pattern you will be able to get a twin pattern. Micro twins will give rise to a diffraction pattern similar to twins. From that we can say that though we see some fringes, okay, this is essentially is a micro twin which we are seeing it. Okay. This sort of analysis has to be done. Any questions you have? If there is no question, we will stop it here. Okay.